We hope you had fun during these 2 weeks we have spent together. And that's the last day for the tutorial, for the tutorials, the lecture. And of course, we will still be online on Discord to answer all the questions you may have regarding the project, the challenge. So for today, for the second time, we will have Shantanu. He was already in the week. So for today, he will introduce us another interesting tools for designing and modeling quantum superconducting quantum circuit. That is JAX Quantum. So Shantanu Rajesh is a co-founder and CEO of Boston Quantum, and he's also a PhD student in electrical engineering and computer science at MIT, where he's part of our engineering quantum system group. So Shantanu, you can take it over for now.
Yeah, thanks for the kind introduction. Excited to be here for the second part of this talk. Today's talk will be very much a tutorial, so a few slides and a lot more code. If y'all are interested in following along, then you can go to .com/JAX Quantum QC Sys and Bosonic. So if you go to just github.com/equus/JAX Quantum, maybe someone can also post this in the Discord as I go through this talk. If you go to these 3 links, then in the tutorials folder of each of these repos and within the talks folder, there will be a notebook. And these are the notebooks that I'm going to be going through. And it's a similar structure in each of these repos. So you can find this tutorial repo that looks like Superconducting Hardware Workshops Fall 2024. Can one of the moderators maybe paste this in the Discord? Great. Yeah, so we can get started. For anyone who wasn't able to join yesterday, my name is Shantanu. As Alex said, I am a PhD student in the Engineering Quantum Systems group at MIT, and I spend a lot of my time thinking about quantum error correction and how do we build quantum computers that are more robust, on which you can write more complicated quantum algorithms and programs to do more cool things. And so today, what we're going to be talking about is a lot of the software that helps enable that research. In particular, a suite of software tools that I developed as a part of my experimental research based on JAX, which is this framework developed by Google, or now maintained by Google. Y'all may have heard of TensorFlow. This is similar in that it helps to accelerate whatever code you write in JAX on GPUs and TPUs, and it is also auto-differentiable, meaning that you can write any function in JAX, or any function you write in JAX, the output of any of these functions, you can calculate the derivative of that output with respect to any of the inputs to that function, which can be quite useful. There will be 3 different software packages that we will discuss today, called JAX Quantum, QC Sys, and Bosonic. JAX Quantum is, excuse me, like QTIP, but with JAX. And so you can very much just import JAX Quantum as JQT and use it as you would QTIP. QC Sys is like SC qubits. It's built to simulate and calculate metrics regarding superconducting circuit elements, and also systems constructed of many of these superconducting circuit elements. It's also built in JAX, And there's also support for periodic drives using flow K3. And finally, we have bosonic, which is a gate simulator for circuits built of bosonic qubits. And so you can think of this as Qiskit, but for bosonic qubits, um, in which you can, for example, create circuits made of cat qubits, binomial qubits, GKP qubits, and so on, and implement different pre-built gates as well as custom gates on these systems, and you can simulate the dynamics of these circuits just under unitary evolution or Hamiltonian evolution, as well as with loss, which is quite useful in simulating these circuits. You can pip install these tools, but I would actually recommend going to the repos, which were hopefully linked in the Discord. If not, you can just go to github.com/equus/jaxquantum or bosonic or QCSys, or just look them up. Go to the GitHub repos and install from source. That should be the most up-to-date, cutting-edge version of these libraries. And that should, if you do that, then you'll definitely be able to follow along in these tutorials. And we periodically update the versions that are on PyPy. So by install from source, I mean pip install dot after actually cloning the repos. And yeah, once you do that, then you'll be able to simulate, for example, circuits like this one, which is this circuit that I showed yesterday, which allows you to stabilize the GKP code. The GKP code is code qubit. This logical qubit is stored inside this resonator, and we use this control qubit to achieve universal control over this resonator and to do things like error correction. And to do just one iteration of this, you can see it doesn't take that many lines of code. It's built very similar to Qiskit in that you have a register of these bosonic qubits. You can create a circuit out of this register, and you can add gates. So we're adding, for example, conditional displacement gate. That's this first one, and a qubit rotation, then a conditional displacement, qubit rotation, and a conditional displacement. And then we can actually simulate the dynamics under loss. So you can see this collapse operator is just single photon loss. And it's really as simple as that. And then we can simulate basically stabilization under single photon loss. And we can, run these simulations and get animations like this one, where, we start off from the vacuum state and we run this circuit over and over again. And in doing so, we actually cool down to the logical code space, specifically to the maximally mixed logical state. And so, again, this is a recap of the topics I covered yesterday, but the way this error correction works is you can imagine errors as, this water kind of coming into the system, and quantum error correction is cooling the system. It's dumping out that entropy that's entering from these errors at some other rate. And for break-even error correction, we want this quantum error correction rate to be larger than the rate at which these errors are actually coming in, so that we're able to cool the logical qubit faster than it's getting heated up by these errors. So that was kind of just like a recap of what we talked about yesterday. Any questions before I proceed?
No, no.
Cool. Then I'll keep going. Yeah, that was just a recap of what we talked about yesterday. Now let's get into each of these packages. So let's start with JAX-Quantum. So here's an example of how you would set up a typical master equation simulation in JAX-Quantum. It's very similar to how you would do this in QTIP. You'll, of course, import the actual package. You'll set up some parameters, some initial state, some times across which you want to evolve the system. Then in JAX-Quantum, you specify the time-dependent Hamiltonian by literally just writing down the function that gives you the Hamiltonian at any given point in time. So in this case, what we're doing is we have our sigma z for our qubit, and then we have a transverse drive, sigma x drive, and that has some time dependence. And yeah, then we can do a master equation solve. In this case, our collapse operator is actually empty, and so we could have just done a Schrodinger equation solve, SE solve. But you can choose whatever you want. SE solve would be faster in this case, actually. And yeah, and then you can just run SC solve or ME solve, and you'll get the states at these different points in time. And you can make a plot like this one, which takes the qubit from ground, initial state, to excited. This is a bit of an old benchmark, and so I think things have updated, been updated since then. But this is just benchmarking JAX against the likes of QTIP, Julia, and JAX itself. What I'll say is JAX makes it really easy to run this code on GPUs and TPUs. And it's also auto-differentiable, which we'll talk about later, which I think are the key advantages. I think if you write correct QTIP code, it should run ideally just as fast after it's kind of compiled. If you write the Python version of QTIP code, it should run roughly as fast as JAX might run on a CPU for at least one solve. I think JAX can have advantages when you vectorize it across, let's say you want to do many simulations at once, then JAX can be really helpful. And although there are a lot of numbers here, I wouldn't actually pay attention too much to these numbers. I have found in my experience over the years that JAX is well suited to some problems, but not all problems. So, for example, sparse matrices, very sparse matrices, are not as well suited to JAX because they're not as well suited to GPUs in general. It's hard to run accelerated code on sparse matrices on GPUs. And so maybe using just like a sparse format instead of running on a CPU would be better than running it on a GPU. But for matrices that aren't as sparse, or if you're able to create a dense format of like a large system that would otherwise be sparse, if you're able to make it smaller and dense, then you can generally see at least as fast of a performance on JAX, if not faster. And when you move to GPUs, you can get an additional speed up. So I would say this is not like a hammer for every nail, but it is something that I've seen speed ups in my personal experience, and I would encourage y'all to try and see if you can see speed ups for your own simulations. The other thing I'll note is JAX has this really nice functionality where we're able to take a gradient of whatever function we create. So if let's say we have this function where we're basically controlling the drive frequency, and what we're doing is we are returning how well did we actually reach the excited state after doing this pi pulse for like a fixed amount of time. Our intuition says that we should drive on resonance to do like a full pi pulse from 0 to 1. And what's cool is that if you throw this into an optimizer using the ability that you're able to actually calculate these gradients, you can use now optimizers with gradients. Then indeed you can optimize this sort of like final time sigma z loss function to take you to -1, to take you to the excited state, and the optimal frequency that it finds is essentially on resonance to the qubit, which is cool to see. So you can, this is a very simple example, but you can get quite creative in the optimizations you do, and which are possible given that it's so easy to calculate a gradient for some like metric function that some function that you create using this JAX code. And so now let's actually switch to code. We'll start with JAX Quantum, and then we'll move on to the next package, just to help communicate the things that I've been talking about. So again, this is in the JAX Quantum repo. Maybe I'll just take a really quick moment to talk about how to install all these packages. So again, for example, for JAX Quantum, and this would be the same process for all of these packages. Go to this repo. Each of these packages also has some docs. You can go down to, in this case, there's just an installation section over here. And I would install from source in editable mode. So after you've installed this repo, run this command, pip install -e, and then you don't even need the dev and the docs, but at least just have the dot in there. And this will install the package using the source files that you cloned, the most up-to-date files. And once you have this package cloned, then you'll see that in the tutorials folder and in the talks folder, there's a notebook. And that's the notebook that I'm going to be using. So I'll keep going, but I'll just mention that. Okay. So yeah, so we can import JAX Quantum as JQT. Again, use it in a very similar way. I will say though that JAX Quantum is quite lightweight, in that it doesn't have everything that Qtip has, but it's very focused on doing what it's designed to do, which is set up these systems and simulate these systems. But if there's any need to go to use some functionality from Qtip, it's very easy to convert from a JAX QArray object to a Qtip Q object. And I'll show you how to do that later. But first, let's just talk about JAX. So here, what I've done is I've defined this function, f of x, which is just taking the sign of x. And JAX is itself an accelerated computing library. And so it has a lot of these tools like NumPy and SciPy, and you can use them in very similar ways. So you can import jax.numpy as JNP instead of import NumPy as NP, and you can use it in a very similar way. So now we've written this function using a JAX function, and we can actually take the gradient of this function by just doing grad of f, and then we can vectorize this function by doing vmap, meaning that if we just had this f of x function, grad of f would work for a single value, and you can see that the gradient of the sine will be cosine of x, and so cosine of 0 will be 1. And so it makes sense that f of 0 is 0, and the gradient of f, which is basically df dx of 0, is 1. Vmap allows you to run this grad f function not just on a single input, but actually on an array of inputs. So for x values going from 0 to 2 pi. And so, yeah, we can run this, and you can see that f of x is the sine function, and df of x dx is cosine function, as expected. So I think this is quite cool. Essentially, what's happening under the hood is it's taking this um, uh, it's taking this f of x function and it's compiling it to XLA, which is essentially this accelerated linear algebra format, which you can think of as the basic operations on whatever hardware you're running on. And so the sine of x is now deconstructed into like some basic operations on the hardware. And that might not even just be, a sine of x like kernel, like block or whatever. And for each of these blocks, we actually know their derivative. And so if you have a function that's constructed of all these blocks and you know each of their derivatives, then you can use the chain rule to figure out what is the derivative of the entire function. That's generally how auto differentiation works. It's different from symbolic differentiation in that, we're not writing down sine and converting it to a cosine just symbolically. And it's different from numerical in that we're not, to calculate the derivative of zero, we're not looking at like 0 plus epsilon, calculating f of 0 plus epsilon minus f of 0 over epsilon. That would be numerical. Auto differentiable is essentially just using the chain rule. The other thing I'll note is there's this concept of just-in-time compilation. Essentially, what this means is that the first run of your JAX function, your JIT compiled function, will be a little bit slower because it's compiling it into this, optimized XLA format. And then future runs will be much faster. So you can see the first run was maybe 23 milliseconds, and then future runs were 36 microseconds. Almost a thousand times faster. Let's see if this works. That's fine. This is basically just code to show you what the XLA format actually looks like, but we can move on. Any questions about JAX? Because these are the concepts that will keep coming up as I show you these different packages, 3 concepts, auto differentiation, with this grad, vectorizing with VMAP, and just-in-time compilation with JIT. I guess there's no questions, Alex?
No, not for now.
Okay. Okay, yeah. All right, so now let's go to the example of velocity harmonic oscillator. And so in this this is essentially just a quantum harmonic oscillator. You can see that the h of t, the Hamiltonian function, is really just omega a dagger a, and is a dagger a. And so this is just the quantum harmonic oscillator potential. And our initial state is the vacuum state displaced by a little bit. And that's also known as the coherent state. And what we expect actually to happen, I can actually show you in an earlier plot that I showed yesterday. This is basically what the coherent state looks like. Under a quantum harmonic oscillator potential, we expect this coherent state to just rotate in phase space, where this is the momentum position space. And so this sort of behavior is actually quite close to what you might expect of a harmonic oscillator in the classical landscape, where imagine you have a ball on a pendulum and it's swinging back and forth. Then you'll get to these points where you'll have the most position, but the least momentum at the top of the swing. Then you'll get to the bottom of the swing, you'll have the 0 position, but you'll have the most momentum. And then that cycle will continue. If you were to draw that in phase space, it would look like a circle. And so this is very similar to that sort of classical harmonic oscillator, but it has a little bit of width to it. And that comes from its quantum nature, its uncertainty in its position momentum. And the additional thing that we have here is loss. So this is single photon loss. Um, and in that case, what we expect to happen is as we, let this quantum harmonic oscillator evolve, it'll slowly sink into the center of phase space. And that's actually what we see happens if we plot these are just, this label is wrong. This should be the imaginary component. Also be careful about running a lot of this code because I think when I have Zoom on, things get a lot worse. So I might just show these notebooks which are already run. But what we see is, okay, this is the real and imaginary component of the expectation of the um, annihilation operator, which is a stand-in for essentially the position of momentum. And so you can see that things are oscillating between position and momentum, but these oscillations, they die down as the coherent state sinks to the center because of the single photon loss. Another way to look at it is if you look at the average number of photons in this oscillator, that decays as you go to longer times. Cool. Now let me show you an example of where you might want to use VMAP. So this was just an example of how would you set up something in JAX Quantum. Again, very similar to QTIP. You can run this on your own notebooks to get a feel for it. But now let's move on to another example. Here we're doing a time Rabi chevron, and that's essentially you just have a sigma z, and you are driving. You have a transverse drive, and what you're doing is you're sweeping the frequency of that transverse drive. And so when you're on resonance, then you'll see these really nice oscillations around the Box sphere. But when you're off resonance, then the frequency of oscillations gets faster, but you also don't go all the way to the bottom of the Box sphere. And so this is a common experiment we do in an experiment to actually figure out what is the frequency of our qubit, right? We'll do this time Rabi chevron, and when we see this sort of pattern, we know that the center of this pattern is our qubit frequency. And so, yeah, so the first implementation of this is just in QTIP. And here I've just timed it in QTIP, so start time, end time. And you can see that the elapsed time here is about 3 seconds to run this. And what is actually happening is that for each detuning, that's essentially a different frequency of our drive. And each of these vertical line cuts is a different master equation simulation because it involves a different Hamiltonian. So in JAX, what you can do is you can just vectorize this and just do all of these in parallel. And so in JAX, you'll set up something that looks very similar to in QTIP. You'll have this h of t function, which looks like h naught, which is just the sigma z, plus h1, which is this omega over 2 sigma x times cosine omega t, where omega, lowercase omega, is being varied as you change delta. And so if you just run this, the first run again is kind of slow, but any future run is much faster. It's 57 milliseconds, as you can see on average. And to be very clear, this is essentially calculating all of these points at once. So what have I done here? I've done a VMAP over deltas. So now I can essentially calculate all these evolutions for different deltas in parallel. Then I've jitted that. And just a note, always jit after you VMAP. Otherwise, you might get a slower function. So always jit after you VMAP. And then I'm just running this for the first time, but then I'm running this after it's been compiled. it's much faster. So it's 59 milliseconds versus the 3 seconds that we saw in Qtip, which is cool to see. And then you can just plot this, and you get the same plot. So cool. Yeah, so that's cool to see. I'll also note, let's see. And in Qtip, I did try to use the fastest Qtip version, this sort of Python version. Yeah. Okay. Yeah. That's it for the JAX Quantum side. It's really simple. It's probably the simplest out of all these libraries. It really just does what it needs to do, which is be able to create these essentially just stand in for Qtip. And just to give you an idea of, exactly how that works, um, we can look at the fundamental building block of JAX Quantum, which is a Q array. Now this is very similar to a Q object. It just stores some data in terms of JAX array, and then it has some dimensionality information so that you can do things like this. So this is doing a tensor product between a sigma z and an identity. And you can see that the Hilbert spaces are increasing in the ways that you expect. So even though the data has a 4x4 shape, this dimensionality information is really important. And this is what distinguishes, this state from some other state in, or this operator from some other operator in like a 4-level system, some other 4-level system. Cool. Before I move on, any questions about the JAX Quantum side, Alex?
So one participant, he wants to know if there is any integrated development environment that we can use for JAX Quantum.
You can use whatever IDE you want. I like VS Code for like everything, but there's not any particular, it's not tied to any like IDE. So I like using VS Code. That's what I'm using right now. But you can use whatever you want. And this is a Jupyter notebook within the VS Code. Cool. Anything else?
No, there's no
Cool.
question now.
Otherwise, yeah, I'll move on. So now let's move on to bosonic. Let me full screen this again. Bosonic JAX is its previous name. This is an older slide. It's now just called bosonic. And again, this is like Qiskit, but for bosonic qubits. And so we support a number of qubits, most notably the GKP code qubit, the CAT code qubit, and the binomial code qubit, and then just normal 2-level system qubits. And you can construct essentially circuits where, for example, here I'm putting a phase rotation gate on I'm constructing a circuit of a GKP qubit and a 2-level system qubit. And now this is something that I might be particularly interested in because I think about GKP qubits and then a control qubit controlling that information and doing error correction. And so this is a circuit that I care about. And what I'm doing is a phase rotation gate on the GKP qubit, and then doing a control displacement gate on the GKP qubit, where I'm displacing the GKP qubit control dependent on the state of the control qubit. And I'm also doing an X gate before these things. So I have an X gate, then a phase rotation gate, and then a CD gate. And this is how the states start, and this is how the states end. You can see that there's a little bit of a rotation on the GKP qubit, and it's also displaced by a little bit. And it's displaced to the left because we did an X gate on the control qubit, which you can see in the block sphere. Over here, we go from this ground state to excited state. Because we're in the excited state, we push to the left instead of pushing to the right. And yeah, you can do unitary simulations, which are quite fast because it's really just matrix multiplication, and that is quite fast in general in JAX. And it gets even faster if you go to GPUs. And then you can also do a Hamiltonian level simulation, where you might set up some Hamiltonian. For example, in this case, we have this Hamiltonian with a dispersive coupling and a Kerr term. And we are simulating a kind of a custom gate here, a number split conditional displacement gate. And we can actually see how this gate is evolving over time. So as opposed to a unitary simulation where you're just acting on the system with an operator, this is evolving the system through some Hamiltonian over time. So we can go to the bosonic notebook now. And again, this is in the bosonic repo. Clone that repo, pip install dot to install bosonic. And then go to the tutorials folder, and within that, the talks folder, and you'll see this notebook called the Bosonic Superconducting Hardware Workshop Fall 2024. And we can, run through this notebook. So again, we go through our imports. You can create these qubit objects. And here I'm just plotting the code states, sort of the cardinal states on the logical block sphere of each of these error correcting codes. And you might have seen the cat codes Wigner plot before. This is what the binomial code looks like. And this is what the GKP code looks like. Yep.
Yeah, sorry, maybe before you go for this one, I have this question that came late regarding what you said before. He said, to calculate the error, we measure the displacement and loss of photon in JAX quantum. If yes, how do we calculate? He said, to calculate the error, we measure the displacement and loss of photon in JAX quantum. If yes, how do we calculate that?
So I think this is referring to how we do error correction. And that is just a particular kind of circuit that you might run, right? JAX quantum is like Q-tip, right? Like you can run whatever you want and simulate whatever you want in Q-tip. But if you're looking to do that particular thing, which is mapping errors from the GKP code to the GKP qubit from the resonator to the control qubit, then you would implement something that looks like this. And this would essentially map the errors from the GKP code to the control qubit, and then there would be a reset actually. There would be a reset after running the circuit, which would dump out this sort of entropy that you've mapped onto the control qubit. Cool. So I'll keep going. So yes, you can create these registers of a GKP qubit and a just like a two-level system qubit, POC qubit. You can create a circuit out of this register, and then you can do a unitary simulation of just doing, let's say, logical X gates on both of these qubits. And you can see that this state corresponds to the minus Z state, where we have the alternating blue and red dots along the y-axis. Because we've done an X gate on our GKP qubit, which starts off in the ground state. And then this looks also like the excited state because we've done a X gate on the POC qubit that starts off in the zero state. Cool, and then we can do, this is the same simulation that I showed on the slides, phase rotation gate, conditional displacement gate. And again, we get this rotated, slightly displaced state. And finally, we can actually simulate the same thing that we did, phase rotation, conditional displacement, but let's say we had a little bit of Kerr. And so Kerr is essentially this frequency shift that depends on the energy in the system. It's like this fourth order term, which looks like A dagger A, or however you want to order it. It looks like yeah, a frequency shift that's dependent on the number of photons that are inside the resonator. And so what this does is it actually distorts the state. And so if you were to run this circuit within, this always on curve, what we would see is we do still do something that's well, actually, it's quite different because this curve is so large now. This is like 1 gigahertz curve, which is insanely large. And so there's not only a distortion, but there's also another rotation. Oh no, actually, in this case, there's no. I think the best way to compare this is to actually remove the X gate here. I think with zoom on, everything takes a lot longer. But essentially, the only thing that happens because of this curve is you can see this distortion. So this state looks really messy, and so that's actually another point to know that we actually don't like curve in these very linear oscillators because they distort states. Um, yeah. Okay. Yeah. So that's about it for the bosonic side as well. And next, what we'll talk about is the QC-sys side. And so I think this is the most um, uh, I think, perhaps one of the most relevant packages. I think it's between JAX Quantum and QC-sys for this workshop. Again, QC-sys is all about simulating superconducting circuit elements and systems constructed of these elements. And so in this notebook, which is again in the tutorials folder, and within that the talks folder, and within that this notebook on the QC-sys repo that was linked, you'll find this notebook. And in this notebook, we're going to go through something that I personally think is quite cool. We're going to go through a system of a resonator coupled to a fluxonium. And so this is actually quite similar to the system that I was talking about yesterday, where we have this 3D cavity, 3D resonator, and we have a fluxonium chip coupled to that 3D resonator. So it's very similar to that, just slightly different parameters. And so what we can do in QC-sys is we can first just create a resonator with a frequency of 4.134. Here I'm just plotting the wave functions, and so you can see this potential is nice and quadratic. The wave functions are nice and equally spaced as you would expect for a resonator. Then you can do the same thing for fluxonium, and here I'm biasing this fluxonium at off of sweet spot. And so we see this double well potential, and we see that the ground and excited states are pretty well isolated within each of these wells. And so the ground state is this blue, and the excited state is this orange. States above that are not as well isolated. These are the plasmon states, the F and H states. You can see that they kind of live between these two wells. And what you can do is you can actually park your resonator in between the transition frequency from G to F and E to H, the two plasmon frequencies. And if you do that, what you're going to see is actually something that's quite cool. And to see that, first, let's construct a system where we have a resonator and a qubit, and they are coupled together, capacitively coupled together. And we can set up the system. We can set up whatever couplings we want, but in this case, it's simple. It's just a capacitive coupling between this resonator and this qubit. We can calculate the eigen values and eigenvectors of the system. And using that, we can calculate something called the dispersive shift. as well as the other metrics like the inherited curve. The dispersive shift is essentially, and I think you've probably heard about this in past talks. It's this term that looks like chi sigma z a dagger a. It's a shift on the frequency of the resonator conditioned on the state of the qubit, and a shift in the state of the qubit conditioned on the number of photons of the resonator. I like to think of it as, at least in this dispersive limit, the coupling between the resonator and the qubit. And so when this goes to zero, you can think of the resonator and the qubit as being uncoupled. And so one thing we might do is we might actually sweep for our particular fluxonium and resonator system, we can sweep across the external flux that's going through the fluxonium. And then we can actually plot the dispersive shift as a function of this external flux. And so this is 0.5 flux quantum means pi flux going through. 0 means 0 flux going through. 1 flux quantum means 2 pi flux going through. And because of the nature of the fluxonium Hamiltonian, there's symmetry points at 0 flux and at half flux. And so you can kind of see at 0.5 flux, there's this symmetric behavior on how the dispersive shift behaves. But one thing that's really cool is that as you change the flux on the fluxonium, you can actually go through this 0 chi point. And this is really interesting because you have the system where you have a fluxonium and you have a resonator, and there's some capacitive coupling between them, right? This fluxonium is literally just stuck into the resonator. But by just changing the flux that's going through this fluxonium, we can actually effectively decouple the fluxonium and the resonator. Yeah, that's something that you calculate, and that's something that you can calculate quite quickly with JAX quantum and with specifically with QCSys. The other thing you can calculate is the Kerr, and so the Kerr in this case is quite small. We're looking at two things: the average Kerr, so the Kerr when the qubit's in the excited state, the Kerr when it's in its ground state. This is again the nonlinearity on the harmonic oscillator potential because we've coupled something that's very nonlinear, the fluxonium. We inherit a little bit of that nonlinearity into the resonator, and we want that to be very small. And for this particular system in parameters, it is. The average Kerr is quite close to 0 hertz. The delta Kerr is a little bit larger. It's on the order of tens of hertz, but it is something that we could, for example, like echo away by doing some pi pulses on the qubit. The final thing I'll note is that you can, because these are all JAX functions, in this case, this calculate metrics function, what it does is it returns the chi and Kerr. That's what it returns. Those are the metrics it returns for the system. And what it takes in is the external flux on the fluxonium. And so what we can do is we can take a derivative of these parameters that are coming out, the chi, the Kerr, the resonator frequency, and the qubit frequency. And these are the frequencies of like the coupled system, right? Not just the bare resonator, but what is the resonator frequency dependent on the state of the qubit. Because it's coupled to this other system, its frequency changes. And what we can do is we can actually take a derivative of the frequency of the resonator with respect to the flux that's going through the fluxonium. And now this is really interesting because this is essentially d omega of the resonator, d the flux bias on the fluxonium. And if you take that quantity, that derivative, you multiply by the flux noise amplitude, the amplitude of noise on that bias, then what you get is effectively this dephasing time limit because of the noise on the fluxonium. And we see that if we just calculate what that limit is, it's about 30 milliseconds, and that's quite high. and should not be limiting. Dephasing on these, even these 3D resonators would be on the order of maybe like, um, well, okay. This should not limit the T2 of the system because the T2 of the system would be limited by the T1 of the resonator. And the T1 of the resonator would be about a millisecond. And so this 30 milliseconds would be much larger. But the thing I want to emphasize is that, we're able to very quickly calculate this noise limit, which would otherwise require a lot of, analytic calculations to figure out, okay, what is the dependence of, like, what is the limit that noise places on our resonator for some coupling to this fluxonium. But in this case, we're able to really quickly do this auto-differentiated gradient calculation to very quickly calculate this coherence limit. So yeah, I'll end there. That's the end of the tutorial. That's the end of the QC-SYS tutorial. There's another slide that I want to mention before I go to that. Any questions about QC-SYS, bosonic or JAX quantum?
Yes, there is one question regarding the boson. He said, during Hamiltonian simulation, how do you deal with the ideal qubits in bosonic gas?
The idle qubits, like the other qubits that, well, the Hamiltonian is defined for the whole system. It's a good question. So if the Hamiltonian is just coming from the gate, then we assume that there is essentially identity or Hamiltonian of zero happening for these other qubits, but the time of the gate will determine kind of the time that the identity gate happens for these other qubits. So let's say I'm doing a conditional displacement gate between a GKP qubit and some qubit. And there's another qubit. However long that conditional displacement gate is taking, let's say 100 nanoseconds, or 100 nanoseconds. Then this other qubit, which is not getting affected, it's going through a Hamiltonian of h equals 0, but it's going through whatever loss mechanisms we've set for that qubit. So if we have, let's say, a bit flip, or like erasure loss channel, whatever loss channel on our other qubit, then it will undergo that loss channel for however long that gate is running. Yeah. And similarly for any other Hamiltonian that we define, like if there's some static Hamiltonian that's always on, then these idle qubits, or these qubits that are not involved in the gate, will undergo the Hamiltonian simulation. Of course, this is not the only way to do this. I would say out of all the three packages, bosonic is probably the least mature. I think QC-SYS and JAX quantum are a little bit further along through testing and through like other people using it. Not as many people have used bosonic. I think one like clear question is, okay, what if you wanted to do gates in parallel, right? How would you do that? There is a way to do it. It's not as straightforward. So I think there's a lot of work that needs to be done, but that work is mostly motivated by the users. So if there are use cases for different kinds of things, I mean, let me know and we can implement it, or you can implement it yourself. Yeah.
I have this other question. The estimate of the noise limit for fluxonium qubit and transmon qubit, is it the same in bosonic gas, or there's a difference?
So the fluxonium limit here is first in relation to QC-SYS, not to bosonic. But this particular calculation you wouldn't do for a transmon. This is, by the way, this is just one of the limits. This would be limit from like noise on the flux line of the fluxonium. For transmon, you don't have a flux line, right? You have a charge line. And so you could do maybe like some sort of calculation using that charge operator and calculating some derivatives, and looking at noise that the um, um, for example, noise coming down that drive. But it wouldn't be the same calculation. But for a tunable transmon, where you do have a flux bias that affects the Hamiltonian, then yeah, it would be a very similar calculation. Yeah. Any other questions? Otherwise, I'll just mention the final slide and we can end it there.
Yeah, there's one. In the last notebook, could you elaborate on how you modify the harmonic oscillator so that the anharmonic oscillator would appear? That is, could you describe what function you use and what parameters you put into the function?
So the system that we're creating here is that of a resonator, this harmonic oscillator, and a fluxonium, this like very nonlinear circuit element. And we're coupling those together. And by coupling these things together, the resonator inherits a little bit of nonlinearity from the fluxonium, which changes its properties slightly. And there's also like a coupling, right, that exists between the resonator and the qubit that determines the dynamics of the system. That coupling is mostly characterized by this chi. So in the interest of time, I'm going to quickly mention the last slide here. Before I do, maybe this is a question for you all. I was asked to send over some like project ideas. Can I mention those project ideas briefly in the slides, or is it something you're going to release later?
Yeah, you can mention that. We will release it after this talk, but you can mention that.
Okay, cool. So I'll just take a minute to quickly mention it. There are like two project ideas that I'm like particularly excited about because I've been thinking about these myself, just for fun. And then there's a number of like smaller project ideas that I sent over to Wakar that maybe you can share with y'all. But I'll just talk about these two ideas first. The first idea is has to do with arbitrary quantum operation construction. So a lot of times people think about, universal control as being able to do any unitary operator on a system, right? And the question is, okay, I have this set of gates that I can do on the system. How do I use these set of gates, put them together in different ways to do some sort of unitary operation I want to do on the system? But often the thing you want to do is not just unitary. So in general, a quantum operation doesn't have to just be this unitary thing. It can involve things like dissipation or decoherence or whatever else. And in general, a quantum operation is described by, a Krauss map that takes you maybe even to like a mixed state, right? It doesn't just leave you in this pure quantum state. And so this first project is about arbitrary quantum operation construction, essentially extending to beyond unitary quantum control and using measurements to achieve that. So there's this really nice paper that you can look into, which shows that if you use measurements, you can actually implement whatever Krauss map you want on a system if you have universal control in terms of unitary control over that system. So if you have unitary control and measurements, you can do an arbitrary Krauss map arbitrary quantum operation. You might ask, okay, why would we want dissipation? Quantum error correction is a great example, right? Those circuits that I was showing you were essentially dissipating into the code space. And so one of the first GKP break-even paper, it did exactly this. It used measurements and resets to do quantum error correction. So I think there's a lot of potential in having a tool that with which you can realize any arbitrary quantum operation. So that's the first project. The second is about measurement-free topological quantum error correction. So we talked a lot about how resets can be used instead of readout for bosonic error correction. Can you do the same thing for something like repetition code or a surface code? Instead of reading out syndromes, then decoding and then doing something, could you just use resets? Um, that's an open question. I don't know if that's possible. There's some like papers out there that suggest some like measurement-free surface codes that came out very recently. I haven't looked into those yet, so maybe the answer is in there. But like even for the simplest system of a repetition code, can you do this sort of measurement-free error correction? So I'll stop there. But I think Waqar will send over some more details about these projects. Cool. Thanks to everyone for your attention and for your questions.
Thank you, Shantanu, for this talk, for this introduction, and also for all your time yesterday and today.
Yeah,
Okay.
my pleasure.
I think everyone, that was it, the last talk of this lecture series. Now we wanted to give you more time to focus on the project and to be focused on that and to deliver the best project ever. Waka, maybe you can take over and maybe explain again in the next 2 minutes before we close the session.
Hi everyone. Is my screen visible?
Yeah.
Okay. So I'm just gonna make them public. You will see them in the Discord. So these are the projects we have come up, like Alex said, with Shantanu, with everyone, the best project possible for you guys. So you can choose projects from here, and you can mention those names in the Google form that I will show you in a minute. You can use this Google form, and we'll also link it in the Discord as well. The important part is that please follow the rules and guidelines that we have been telling you from the very start. Uh, and also, you can find some references, some papers, some things that you can look into and get started with these projects. If you need additional material, additional resources, you can text us in the Discord channel that we have created for you, and we will share that resources to everyone to see, so that you can all get equal chance of doing amazing work. So when you click on this link, you will get onto the Google form, where you will be required to enter your full name, your email address, Discord ID, and GitHub profile. Please make sure that you enter the correct information, because we will create the repos for you based on your information. You can create whichever name you want for your team, and then also mention all the complete details of your team, because we will also want to add your teams into the GitHub repo that we'll create for you. And you can mention the project's name here, like project 1, 2, 3, or whichever project you want to work on, right? So the deadline is tomorrow, 5 p.m. EST. So please be aware of those timelines, because we will close the form after the deadline. So I wish all of you very good luck with the projects, and I'll see all the amazing work after a month.